The next point I want to make is to solve this system numerically by using the stellar numerical computation engine. But first we need to build the stellar model, and then we're going to simulate this model. So how do we build the stellar model? At the previous lessons, we used the stellar. At this stage, I believe you should have reading knowledge of the stellar. And today, I'm going to show you the step-by-step construction. The first step is construct the dynamics of the flow. And we have two variables. Then the step one, we just draw two stalks and rename the stalk as rabbits and the wolves. Those are the two variables, xt and yt. It's a dynamic, it changes over time. That's the step one. Step two, we're going to draw a flow here and rename as rabbit birth. Let me just put it a little bit. No. And draw a flow outflow here. We call it predation, because that's how it was consumed by the wolf. That's the dynamics of the rabbit population. The second, we do the same thing. We draw a flow here. That's the birth of the wolves. And we name it wolf birth. And then an outflow, we call it wolf mortality, the death of the wolves. That's how the population change, by birth and the death. All right, that's our first step. And the second step, we're going to put the converters, which is the source of information, or say is the 4 parameters. And those 4 parameters, we follow 2 different conventions here. One convention is the mathematics convention. We call it ABCD for the concise of mathematics expression. But another convention is the convention for computer programmer. We write a program for the human being to read. We use a long name called the rabbit birth rate for this A, and the rabbit death rate for this B, consumed by the wolf, and the C is this wolf. Okay, the C and the D I confused here. Is the wolf death rate. I call it wolf mortality rate. And the D is the predated rabbit rate. That's talking about how many rabbits consumed to reproduce one new wolf. So that's the ABCD. That's the information we need to do the computation. And then after you finish this, we're going to put the information to wherever you need to do the computation. But the mathematics model, if you look one more time, here, the first one, AX is the inflow in, and the BXY is the flow out. Then you follow this. Idea. Here is the flow in. You need the AX, so you put the information AX to here. The flow out, I need the BXY. That's why I need the B is here. X here, Y here. That's how we build this flow out. And the third, we have this dy. That's the birth of the wolf. And then that's dy. And the last one is minus cxy. That's the c. Oops. No, cy minus cy. I confused. That's the death rate. The death rate only related to the c, the wolf mortality, and that's the cy minus cy. Now c is here, y is here. And this is dxy, dy, dx. Now look one more time. See, ax, bxy, dxy, and cy. All right, then we completed the model. But this is only the conceptual model. Why is only conceptual model? In Stellar, it's called the map, because there's no quantity here. We do not know what is A, B, C, D, and we do not know the formula. We do not know the initial condition. So the third step, we're going to translate and this into mathematics model. So to change the map into math model, you need to toggle the stellar from the map to the model. That's the third menu on the vertical bar. And then double click all the 4 converters and fill in all the numbers like A, B, C, D. A is 0.2, B is 0.002, C is 0.001, D is 0.25, I remember, if I'm right. And then you need to double click the 4 floors. That's the switch. You double click those positions, and then you fill in those formula. And finally, after you finish these 2 steps, and the last step, you need to fill in these 2 initial conditions. And here you start from 1,000 of rabbits, 45 of the wolves, and then you fill in that respectively. So after you finish this, what you get, we call it a mathematics model. Now you are ready to run and simulate the model. So how do we do that? We need to go to the run spec. That's on the top menu, and you select the run spec from the run menu, and choose the right algorithm. That's all our algorithm, rank kata 2, rank kata 4. I think that's the best. That's rank kata 4. The default time is 12 units, but I would like change to 120 to observe more cycles of the population oscillation. You can count 12 as 12 months, that's 1 year, 120, that's 10 years, if the unit is 1 month. And then I need to display, I double click the graph icon on the top bar, and then fill in the domain from 0 to 120, and the range you need to try, and just make from 0 to 12,000, 0 to 6,000 for the X and the Y. You don't have to fill in, but later on you can change it. Now you click the run button, that's what you see. The domain is from 0 to 120, And the red one is for the rapids. You see, we use different scales. The rapids is the red line, goes almost 11,000 on the peak. And the pink is the wolf population, goes around 5,000 in the peak. And the phenomenon is, as we talked before, the rapids population goes up and down and up and down in cycles. That's about 3 cycles in 10 years. And the wolf population just have a little delay, goes up and down to their peak population each time. Also have 3 cycles. So you see a periodic phenomenon happened, and just like we discussed here. But this information, we call it a time series. Or you call it a dynamics in either way. Depends you learn in computer science degree or mathematics degree. Well, that's a complete cycle for the stellar model and the simulation. A lot of information I'll let you read by yourself. 3 concepts are related with what we are talking today. One is the definition of autonomous system. Any system like this, if you see there's no t on the right hand, only have derivative on the left hand, in those systems, we call it autonomous system. And the only requirement is no t on the right hand. And if you let the right hand equal 0, by the equation, the left hand, the derivative also equals 0. In calculus, we learned if derivative equals 0, we call it a critical point. And you can call this as a critical point too, but most of the time for application, we call it the equilibrium point.